Logarithmic equations are probably the least intuitive kind of equation that you'll ever solve. The reason for it is that we don't necessarily solve them by doing something to both sides of the equation, which is what we do in most cases. But here's the idea. What we want is to start by isolating a logarithm, just like with many of the equations we solve. We start by isolating the piece that has the variable. In this case, I'm going to simply divide both sides by 2. So that part is pretty simple. That leaves me with log to base 3 of x is equal to -1. Now the way I'm going to solve this is by rewriting it in exponential form. In order to do that, I have to identify the base. The base of the logarithm is also the base of the exponential expression. I have to identify the exponent. The exponent in a logarithm is the result. When we find a log, we're asking what is the exponent. So this number over here is going to become my exponent. And in my exponential expression, of course, this is where the exponent goes. Then there's the other piece. Whatever we're taking a log of is the piece that goes on the other side. Generally, if we can identify 2 out of 3 by name, we can figure out where the other piece goes. So in this equation, the first thing I'm going to do is ask myself, what is the base? And I say, aha, the base is 3. I then ask, well, what is the exponent? The exponent is the result of the log, so the exponent is -1. That means that I can now rewrite this whole equation with the base to the power of the exponent, so base 3 to the power -1, and then put my equals, and what I have left is that x, which is the input to the log. By the time I've rewritten this in exponential form, I'm basically done. 3 to the -1 can also be written as 1/3, but there's nothing more that needs to be done here. So what makes these difficult is that we really don't do something to both sides. We actually identify each piece, break the equation down, and reconstruct it as an exponential equation. Now let's take a look at what this process can look like if we have an equation with more than one logarithmic term. We have log to base 2 of x plus log to base 2 of x minus 2. We can use a property of logarithms to combine these and write it as a single log. So that's going to be log to base 2 of, I want to remember that that property tells me I would multiply the inputs. So that becomes x times x minus 2. I haven't done anything to both sides, so that's still just 3. All I did was apply a property of logs to the left-hand side. This is now in the form log to base a of something, even though this something is a bit longer, is equal to a number, so I am ready to rewrite it in exponential form. First, identify the base. The base is 2. Next, identify the exponent. The exponent is the result of the log, so the exponent is 3. Now I'll reconstruct this equation starting with the base 2, taking it to the power 3, and setting it equal to that input to the log, which was x times x minus 2. So I have gotten the x variable outside of the input to the log, and I now have an equation that I can solve. 2 to the power 3 is 8, and I'll distribute in here to get x squared minus 2x. I can see that this is a quadratic equation, so I'll go ahead and get all the terms on one side. And since this looks like a pretty easy factoring problem, I'll go ahead and solve it by factoring x, 2, and 4. And I can see I want the 4 to be negative and the 2 to be positive in order to get the correct middle term. Now setting each factor equal to 0, I get x equals negative 2 and x equals positive 4. But I am not quite done with this equation. So it turns out anytime you apply a property of logs with variables, you lose a little bit of information and you may gain some extraneous solutions. A number could possibly be in the domain of this expression after combining them because we've multiplied some things together, and still not be in the domain of these original expressions. So what I have to do at the very end is check my solutions against the domain. Remember that a log can't take a negative number or 0 as its input. The domain of the log function is all positive numbers. So I don't just look at these numbers and see if they are negative or positive. I have to actually look at them in the log expressions. So looking at x equals negative 2, I can see that I would immediately try to take the log to base 2 of negative 2 if I were plugging that in, and that doesn't work. Therefore, this is an extraneous solution. Whereas with 4, I can see I would be trying to take the log to base 2 of 4. That's no problem. I would also be trying to take the log to base 2 of 4 minus 2, which is still the log of a positive number, so that's no problem. So really my only solution is 4. To check against the domain, either you can find the domain of the original equation, or you can just try plugging these numbers in and seeing if everything is defined. Now there is another form that shows up with logarithmic equations. It's not always necessary to rewrite the equation in exponential form. If we have something that is of the form log equals log, where the bases match, then we can solve it by simply setting the two inputs to the log equal to each other. It's important to take a moment to understand why this works to make sure we're not harboring any misconceptions. For example, here's what we are not doing. This is a really important point. Log to base a of x equals log to base a of y. It might almost look as if it's okay to divide both sides by just the log, right? If I were to divide both sides by log of a, or log to base a, and then just cancel these, right? I'm almost afraid to even put this in writing for fear that somebody will remember it as an okay thing to do. This is a giant no-no, even though it does get us x equals y. We're never allowed to divide by a function name because log is not multiplied by x. Log is not multiplied by y. That's the only context in which it works to divide by a factor and cancel, right? So this isn't really what's going on. Instead, what we're saying is this. It's sort of a background argument. The first part of it is that log is a one-to-one function. We know that the log is a one-to-one function because its graph passes the horizontal line test. Then we know that the definition of a one-to-one function is that we will never get repeated outputs for different inputs. And another way of saying that is it means that log x equals log y, this could be to any base a, implies that x equals y, that it's not possible to take the logs of two different numbers and get the same result. So because log is a one-to-one function, we can just make this conclusion just based strictly on the definition of one-to-one functions. So we're going to apply that to this equation here, but notice that log equals 2 times log is not really the form. We need it to be strictly in the form log equals log. So to get it into that form, I have to use a property of logs to move this 2. The only place it can move is up into the exponent. So I'm going to first rewrite this as log x equals log of 2 minus x squared. Then I use this property and I say, okay, giving myself the argument that because log is a one-to-one function, the only way for the log of x to equal the log of 2 minus x squared is if in fact x is equal to 2 minus x quantity squared. So if our equation is really simple of this form, then it does work to simply get rid of the logs. But this is the only situation in which we can do this without rewriting something in exponential form. So now I have a quadratic equation which I can solve. I have to square out that binomial, so I'll go ahead and do that. And then get all my terms on one side. I'll go ahead and subtract that x to get a middle term of negative 5x, and I'll put these terms in order of descending powers while I'm at it. X squared minus 5x plus 4. This is a very simple factoring problem, x minus 4x minus 1. And therefore I get these two solutions, x equals 4 and x equals 1. And again, because I applied a property of logs, I really should look back and make sure that these are both in the domains of the original equation, not just the equation after applying that property. That property technically only applies if the expression was defined in the first place. But we go ahead and apply it assuming that log of 2 minus x is defined. So we still have to do this step where we check against the domain. So I'll take my x equals 4 and just look at all of the expressions that I would be plugging it into. Log of 4, that's no problem. Log of 2 minus 4, that one is a problem, right? That's going to be the log of negative 2, which is undefined. So I'm going to throw this one out. But checking x equals 1, I can see I would be taking the log of 1. Looking at the left side of the equation, that's no problem. And the log of 2 minus 1 is also no problem because that's the log of 1 also, and 1 is a positive number. So really my solution is just 1. So we can see that it's not always a negative number that gets thrown out. It's something that makes the input to the log negative, which can in fact be a positive number. All right, so in this example we have a sum of logs, so we do have 2 log terms and we have a numeric term. In thinking about whether we should try to get this into a form where we would rewrite an exponential form like our first formula told us, or if this is a situation where we should try to get it into the form log equals log and just drop the logs like we did in our last example, what we're really looking for is, are there any terms without a log? And in this case we can see there is a term without a log, that 5. If we have a term that doesn't have a log in it, we probably should try for the first form. We can combine our logs using a property of logs. So looking at this expression on the left, we will go ahead and combine these using a property of logs. A sum of logs is the log of the product, so 2 times x. And this is the type that we would rewrite in exponential form. We need to identify the base and the exponent and then break the whole equation apart and rebuild it in exponential form, in which case it has no logs. This is a natural log, so instead of looking at it and seeing the base written, we know that it's an implied base e. The result of the log is still the exponent, and so my exponent is 5. Now I'm going to rewrite this in exponential form. Base to the exponent equals the other thing, which is really the input to the log, in this case 2x. So I'm almost done with the equation at this point. All I have to do is divide both sides by 2. And my solution then is e to the power 5 divided by 2. Remember that in order to have an exact solution, I can't go plugging that e to the 5 into the calculator before I'm done. To get an exact solution, I have to put off all calculations involving a calculator, which are just decimal approximations, until the very end. But the very end is now, so let's go ahead and do this. We have 5, and we are exponentiating it with base e. I believe in this calculator I have to do a shift in e to the x. Now I'm going to divide by 2. So I get 74.207 if I round that to 3 decimal places. So this is a very short, simple equation, but it's fairly confusing too. There's a lot of the ideas of what to do with this that had to come from our own heads. There's not a lot of triggers or suggestions in these kinds of equations. So in that sense, they're some of the hardest, even though they might involve very few steps. So as a quick summary, we have 2 different models for logarithmic equations. The first one is the one we would follow if we have any terms that are not part of a log. Here, this y is not part of a log, right? So if you have any terms that are not part of a log, then you want to follow this first model, even if you have to use some properties of exponents first to get it to look like this model. The second only works if the log terms are the only terms that we have, right? So every term in this is a log of something. We might still have to use some properties of logs in order to combine multiple log terms on one side, but if we can get it to the form log equals log, then we have this simpler process, which is just to drop the logs and say the only way for the log of x to equal the log of y is if x is in fact equal to y, so in one step we just drop the logs.